In this video, we're going to do some review of techniques we can use to simplify radical expressions. It's important to know how to do this well because radicals appear throughout all of algebra and higher math. Simplified radicals make expressions much easier to work with, and it's going to be essential in order to be able to solve different kinds of equations later. Let's talk about some key ideas and rules that we'll need in order to solve these. First of all, radical notation is things that are written in the form the nth root of a. So in that expression, a is the radicand and n is the index. What we're looking for here is a number that when we multiply it by itself n times, we get back to a. One of our most important things that we're going to use as we simplify these is this product rule that says that the nth root of a times b is equal to the nth root of a times the nth root of b. Now, generally, that only works if a and b are positive numbers. When we talk about complex numbers at some point, we'll see some cases where the product rule is not true for negative numbers, but as long as, and when n is even. But let's just consider that a problem for future us. And for now, we're going to use this product rule as written. A really important idea is going to be the idea of perfect squares and perfect cubes. There's perfect powers for things higher than squares and cubes, but those are the ones we're probably going to see the most often. So you're going to want to commit to memory the perfect squares, which are 1, which is 1 squared, 4, which is 2 squared, 9, which is 3 squared, and so on and so forth. And then the perfect cubes, 1 is 1 cubed, 8 is 2 cubed, 27 is 3 cubed, and so on and so forth. To simplify a radical, we're going to follow a procedure that will work regardless of how complicated the radicand is. So what we want to do is factor the radicand by finding any perfect powers. Anything that we know in there is a perfect nth power. We're going to factor those. Then we're going to separate out the radical using our product rule. And then we're going to simplify each of the terms using those perfect power terms in particular. We'll look at a couple of examples to make sense of this procedure. All right, we'll start off with a fairly straightforward one. We want to simplify the square root of 72. So notice there's no n value. There's no index written there. When that's the case, then we're going to assume that n is 2. That's a standard practice, that if it's not written in there, it's a square root. And that's because square roots are the ones that we see the most often. All right, so our goal here is to find perfect squares that divide 72. So let's start looking at our list of perfect squares. And I know I'm looking for perfect squares because n is equal to 2. So my perfect squares are 1. That's not ever a helpful one. But then we have 4. Which does in fact divide 72, so we can start by dividing that out. The square root of 72 is going to be the same as the square root of 4 times 72 divided by 4 is 18. Okay, now 18 also has a perfect square that divides it because the next one in our list is 9, so we can write this as the square root of 4 times 9 times 2. The product rule tells us we can then split that into 3 different square roots. 2 is not a perfect square, and then there's no perfect squares that divide it other than 1, which again, not particularly helpful. So now that we have it written this way, we can take the square root of each of these. The square root of 4 is 2 because it's a perfect square. The square root of 9 is 3. The square root of 2 just stays as the square root of 2. And so our final answer is 2 times 3 is 6. We have 6 square roots of 2. All right, this time we have an index of 3. So that means we're going to be looking for perfect cubes. If you ever, I spelled perfect wrong. If you ever forget this list, you can create it by just cubing numbers. So our perfect cubes, we take 1 cubed, that's 1. Again, not going to be helpful to us. 2 cubed is 8. 3 cubed is 27, 4 cubed is 64, 5 cubed is 125, and the list goes on and on. So we're looking for one of these that divides 81. Well, 81, it turns out, is 27 times 3. So 3 times the cube root of 81 can be rewritten as 3 times the cube root of 27 times 3. 3 does not have any more perfect cubes that divide it. It's too small, other than 1, of course. So now we can use our product rule. We're going to split that into the cube root of 27 times the cube root, that's very hard to read, the cube root of 3. The cube root of 27, remember 27 is 3 times 3 times 3, which means its cube root is 3. So we get 3 from the first 3, then we get another 3 here, and then we have the cube root of 3. And so our final answer is 9 times the cube root of 3. All right, in this next example, notice we're not dealing with numbers now, we're dealing with variables, but that's okay, we can use the same idea. So our index is once again 2, so we're looking for perfect squares. The first thing I'm going to do is I'm going to rewrite my expression by splitting up the variables because we have to deal with each of them separately. All right, now perfect squares, when we're dealing with variables, are exponents that are divisible by 2. Right, so we know that y to the 4th, that is its own perfect square because that is y squared squared. Our rules of exponents tell us to multiply. So the second part of this is already a perfect square. The first part, x cubed, isn't a perfect square, but we can rewrite it as x squared, which is a perfect square, times x to the 1st. So now we have this expression. So anything here that has an even exponent is going to be a perfect square. So this is a perfect square, and we have a perfect square here. And so we can split one more time. So we'll get the square root of x squared, then we have the square root of x, and then we have the square root of y to the 4th. And our two perfect squares, we can now simplify them. The square root of x squared is x. The square root of x in the middle doesn't simplify, and the square root of y to the 4th is y squared. And typically we write these with the square root, the radical term to the right. So we're going to rewrite our final answer as xy squared times the square root of x. All right, this time we have something similar where we have, well, here we have a combination of numbers and variables, but this time we're looking for a cube root. So our index is 3. So here, when we deal with variables, if we have things of the form x to the 3rd or x to the 6th, or x to the 9th, each of these is divisible by 3. So if we take the cube root of those, the cube root of x to the 3rd is just going to be x. The cube root of x to the 6th is going to be x squared, and that's because x squared to the 3rd is x to the 6th. Similarly, the cube root of x to the 9th is going to be x to the 3rd. Notice in each of those cases, I'm taking the exponent and I'm dividing it by 3 to get the new exponent. 6 divided by 3 is 2. 9 divided by 3 is 3, and so on and so forth. So we're going to want to split our variable terms up into things that have powers of 3 in them, and then whatever's left over. So the cube root of negative 24. So first of all, negative 24 is negative 8 times 3. Now I did that because this is a perfect cube. Perfect cube because negative 2 times negative 2 times negative 2 is equal to negative 8. So I have negative 8 times 3, and then x to the 5th I can write as x cubed times x squared. That one's also a perfect cube. And then y to the 9th is all by itself a perfect cube. So I have a couple of perfect cubes in here. So now I'm going to split this up. I'm going to write this as the cube root of negative 8, the cube root of 3, the cube root of x cubed, the cube root of x squared, and the cube root of y to the 9th. So the cube root of negative 8 is negative 2. The cube root of 3 doesn't simplify any further. The cube root of x cubed is x. The cube root of x squared, because 2 is less than 3, that does not simplify any further. And then the cube root of y to the 9th, using the rule we have over there to the left, that is going to be y to the 3rd. So we can put all of our perfect terms, or the things that are no longer inside of cube roots, we can move them to the front. So we'll get negative 2 x y cubed y cubed, there we go. And then we can put our cube root terms together and we can put them back into a single cube root to keep things simpler. So we end up with negative 2xy cubed times the cube root of 3x squared. All right, as usual, we'll wrap up with a quick summary of what we've seen here. So we're going to factor our radicand by finding any perfect powers. And we saw that we can do that for both numbers and for variables. We're then going to separate the radical up using our product rule. And then once we're done with that, we know we can simplify the perfect power terms, and anything that's left over is going to remain inside of its own radical.